Okay, I can find the video from Jennifer, so I guess we can just start. So welcome to this session. This is Tracing Distributed Microservices with Rafael here. So Rafael is the author of ByteBuddy, which is a bytecode manipulation library, a code generation library for the JVM. Chances are that if you are working with Java in some kind, you are running his code, very likely. So he's written a lot of Java agent, and this is kind of the main topic of the sessions of this session as well. And Rafael is a speaker, has gone to many conferences, has earned a lot of really nice awards. For example, Java 1 Rockstar, it's a Duke's Choice Award, Groundbreaker Award, and it's a Java Champion, of course, because this is the Java Champions Conference. I think as part of also maintaining ByteBuddy, it also maintains Mockito, which is a library that is used for mocking and testing. So again, I'm pretty sure that most of the people that is attending the session will probably be familiar with that, and therefore they're running Rafael code. So Rafael, the stage is all yours. Thanks for being here.
Yeah, thanks for having me, and thanks for the introduction. Should note that Mockito, we're quite a great team of people, so ByteBuddy is my thing. And today I'm not going to talk about Mockito, but about ByteBuddy, which is a library I've created for the last maybe 7 years, and which is used to implement Java agents partially. And this is the topic, or the application of Java agents I want to talk to you about today is APM, so Application Performance Monitoring, for those not familiar with the term, and how you can implement it on the JVM or how it even works on JVM. And I'm going to switch now to that I see full screen, so you might still see my face, but I can't see if everything's still working, so I hope I'm not going to just speak to my computer like a maniac for the next hour. Right, so just a disclaimer, I have worked for Instana for like a year as a consultant. I've helped them to bootstrap their product in the early days, and which is sold to IBM, or the IBM bought the company. So I'm not really, I haven't worked with Instana actively for quite a while, but I still want to disclose that that's where most of my experience comes from. This is, of course, a color talk towards those experiences. So just that you know that that's the background I have. Right, so what I want to do in this small hour that I have with you, I want to do an inventory. I want to talk to you about what is tracing, what is distributed tracing, then how can you implement it, and how can you basically make some corner cases of it. And the idea of this talk is that you understand how all these products work. You throw into your production systems, and it's not only Instana, it's AppDynamics, New Relic, Datadog. They all have agents, and as a matter of fact, most of them use ByteBuddy, the same library that I want to talk to you about today and the application of it. But I think it's interesting to know how this all works. Also, if you want to debug, especially performance issues of tracing agents. So, the inventory, what is tracing, or why do we need tracing? And to begin this talk, I want to do a little bit of history, and I want to talk about Java EE in the sense, because we've had all this before. We've had very observable applications, and actually, as a matter of fact, this is where Java EE came from. I think people always think that Java EE was mainly targeted at the developer and wasn't a very attractive environment for many of us because it feels kind of constrained. But the Java EE constraints were, or Jakarta EE now, are a bit by design at least, because a nice feature with containerized software, and the early Java programming approach had all this, was that it was standardized. And with Java EE, if these modules, these EARs, talk to each other, you could have a request coming from the web, and it would maybe be dispatched to node A, and node A would talk to node B and to node C. And if something was wrong with the application, you had all these dashboards. For example, here this is WebSphere. You could look in there, and if you zoom in a bit, you can see like what are your web servers doing, what are your message queues doing. You could just click on them and see how your application is healthy, how your application is talking to different modules. It would all cluster together, and you could observe your cluster, right? Because it was using APIs that were observable by the application server. And of course, this isn't necessarily the way we do things today, but the general idea was actually pretty good. You could just throw software in, and your operations teams could observe what's wrong with the software, if there's something wrong with the software, right? But we moved away from this because often this is perceived as very, very hard to work with and difficult to get started with. So the taste of the day is not doing this anymore. But we could see traces. We could see how something came in from a client, walked through our application, and went out again. And if something was slow, we could see exactly what module or what enterprise bean was responsible for it. But with greenfield microservices, this is no longer possible, right? So now we have Java, plain old Java applications. We use Drop Wizard, we use Spring Boot, we use Vertex, we use all these other frameworks that are out there. Might even be natively compiled code and not Java code anymore. And if a web request comes in, then it calls a service, and that service calls another service, and so forth. And if something is slow, now you have more trouble, because now you don't necessarily know where the service has a problem, and this is where distributed tracing comes in. So the idea of distributed tracing is more or less to regain a property of software that we've always had in centralized applications like the Java EE stack back in the days. Right, because the problem is with these microservices, you end up with something that people like to call the Wheel of Doom, and this is just a service map from Halo, and this is one from Tula, where all their services are and how they talk together, and basically the colored lines here are the main roads that are taken most. And if there's something wrong, like reddish here in the picture, then you have to find out what line is the problem in your many dispatches between the single services, and that's of course difficult. So that's also called Death Star topologies, because you typically have still central structures, and observation of services and tracing of service calls is very complex, right? So a thing with distributed services or microservices is that it's often overlooked, is that it doesn't ease necessarily how the software as such behaves, and the complexity doesn't disappear. It just is moved a bit out of the single application and moved to the orchestration of many applications, and it makes operations challenging. And I guess everybody of you who has worked with complex distributed services has run into this, that you as a DevOps team, you spend a significant time of your day tracing manually where something went wrong, and that's something where APM tools try to help you with, right? So, and just a small outlook. So the next big thing is serverless architecture, right? And in a way, it takes this idea a step back to the way Java EE behave, because if you deploy your jars on Lambda architecture, for example, in AWS, then you are going back to standardized APIs. You have to fit your application into the small frame of the application API, and then you get back this observability, right? Now you have your standardized way of running your application again. You don't have this wilderness, this freedom that developers like, but operations people typically don't like. So Lambda it's fairly easy to observe compared to unstructured microservice architectures, but it does, of course, put you back into a frame where certain things are no longer possible, and in a way it takes us a notch back to what we've had as things are in technology, that you always miss the thing that your current preferred stack doesn't offer, right? Yep. But in other than web servers, unfortunately, Lambda architectures typically are vendor dependent and are proprietary. So now we're back at Java EE in a way, but with vendor lock-in. So in this angle is of course a bit too much said, but in this angle, that's certainly a truth in it. So yeah. All right. So how can we achieve tracing microservices? How can we use these greenfield stacks that we all love so much, and still have the observability that the Java EE stack brings with it, and also Lambda stacks often bring with it by having something standardized. And the approach to it is that we have to apply tracing, and tracing is in a way a framework where you trace calls to services, but you don't trace calls to single services. You trace calls to services and transition through multiple layers of an application, where every layer is a microservice, right? So let's say you have this one application, and this is a web server, which is called from the web, right? And this web server will typically call another server, and this server might at some point then call the database. So we have two HTTP layers, and then we have one JDBC layer. So let's say that's a typical middleware. You have like some backend dispatcher for a web page, and then you have an internal service for doing some middleware computations, and then this middleware computations reaches out to a database. And this is the path being followed. And then let's assume that this JDBC layer is having issues. Let's say we're hitting a full table scan for a call, and things take slowly. But the problem here is that if you are observing the system, you will observe that all three layers are slow, and it's not trivial necessarily to see for single calls why single calls are behaving like they are. Let's say you have 1 million calls a minute, and just 100 of them are slow. It's not necessarily easy to see how this all hangs together, because of the pure noise of your log files, of your metrics. It's not trivial to point out the root cause. And this is where tracing helps you, and this is why distributed tracing has become such a huge market. This is why all these companies have blown up so much and have become so valuable in the space, because this is a question as an operations team. If you ever have helped out a company to debug an issue on Christmas times or on Black Fridays, and this is an answer you want to have immediately, and not after digging through log files after many hours. So this is where tracing frameworks have defined certain terms, and I think it's important that we first learn the terms. So a trace collector would then basically collect all these steps of any walk through an application layer, and every application would have an entry and an exit, and this is basically what you record. Let's say this takes 230 milliseconds, fairly long for a shop, for example. Then the first thing you do is you just assign a random UID to this call when it comes in, and you record it from the time it enters to the time it exits. And you will do the same for the next service, and say, all right, this is an entry, and then again you observe something at the server. But additionally to just recording it, when you make a call from the first layer through to the second layer bar, you will inject the current traces ID, which is typically like a UUID. You will inject it as information into the HTTP call, and let the bar server know which call you're currently making. And then you can basically align these two and say, all right, A and B, they belong together because A triggered B. So you can basically combine them. And then you can say, all right, the first thing, this was basically the entry from the HTTP server, and then we have the exit there. The blue dots on the side, this is network latency. That's not necessarily what's causing the issue, because of course there's a deviation from the entry at B and the exit at A. And then you can say, all right, next thing, the JDBC call, this is the exit here. This takes so long. And if you look at this picture, and you know that the MySQL call should normally just take 5 to 10 milliseconds, then now you can tell that it's actually not server foo or server bar that's the issue, it's the database. And that's basically the whole trick of all these frameworks. It extracts this information for you, and the trick is that it makes it convenient, typically by applying it automatically, because of course if you implement something like this, you have to adhere to a format. You have to implement things the same way in foo and bar and every service that you run in your application network to make them interact. And that's the contrary idea to microservices, where you want to give people the freedom to do things you see fit and not to adhere to standards, not necessarily, which basically defeats some of the purpose of microservices. So that's why all these companies try to automate this. And it's basically, of course, you know my background, you know I'm working with Java agents and code instrumentation, as you might guess. And that's what I'm going to show you, how you can use code instrumentation and Java agents to make this problem go away magically. Right, and that's basically what I've done as a professional consultant for quite a while, and I'm going to share these experiences with implementing services like that. But you can already today there's a lot of open source software around it, obviously, as well, and one of the most liked and most well known of this is Zipkin, and Zipkin does exactly that. Zipkin is more or less the backend of displaying traces. So of course, what you've shown here, this is the trace collector. It's typically like a Kafka topic or something, just some backend that accepts data blindly and consumes it as quickly as possible. And that's what Zipkin is. Basically, you have to implement these services to extract this data and to generate it somehow, but then you have to send it in, and Zipkin accepts it and then says, all right, this is a server request, the SR, and the server response and the server send is basically where span ends, and this is a span. Every segment of a microservice chain is a span, and then the outer things are basically including the network latency, are the client send and the client response, and then all spans that belong together, that are part of a chain that share IDs, right, are called a trace. And if you read anything about distributed tracing, these words are everywhere, so it's important to understand what they mean. A span is basically a single segment of a single service, and the trace is the collection of spans that belongs together, forming a single transaction in a microservices system. And the primary task of a distributed tracer is to basically extract as many traces as possible and to display them, and then hopefully show you those that are interesting, because of course if you have millions of requests a second, then you have to find deviations, and that's where you have to decide on a product typically that help you with that. And some do it better, some do it worse. I'm of course saying that Instana is doing quite well because I work with it, and hopefully my ideas were well enough to also help to improve this tracing behavior. But of course you have to make an opinion of yourself, and people have preferences, so I'm not going to try to advertise you something here. Right, so and the nice thing is also that you can add annotations to these traces. Typically Zipkin allows this to you too. So for example, if you have a MySQL trace, then you would normally add an annotation to describe what it is. Best case, you even have the SQL query, or you might even add a query plan. It's fairly free. So typically in the end, you get something like a GUI, where you see, right, there was a trace called client call server via get, and you see that one, and then you see underneath basically where, like a flame graph, right, where the time was spent, and then the longer a bar is, the longer it takes, and the further down it is, the more self-standing is it, like a JDBC call, like the end of a call chain, right? So this is what you navigate, and I think if you have a service architecture with a few more than a handful of services, then basically this is mandatory. Otherwise, you will lose the overview entirely and spend much more time on operations, and it's quite a cost factor. If you have a team of 20 people and 12 of them have to be on ops all the day, then effectively you downsize your team to 40% of capacity. So that's the overhead you're generating for customers, and if operations goes quick, then you open a lot of time. So these investments pay off typically. But how do we get this, right? How do we get information out of an application? And in Java, Zipkin offers a library, or like the pendant to Zipkin for tracing Java services is called Brave. And Brave offers an API, and this looks very similar to a metric API, with the difference that you have to specify what the trace ID is. The trace ID is basically the ID that spans over multiple requests. And then you can say, all right, I have a span, I want to name it foo on the GUI, I want to give it a trace ID 42, and the unique ID 48, and it's of course nonsense. Typically use UIDs. But if this is like the start of an application transaction, like an incoming HTTP call, then this is what you would do. Then you do some hard work. You maybe call some other services, and then you end the span, and you record it and send it to the server. The hard part, of course, is that you have to extract the trace ID on every exit of the application. Every time you make an HTTP call, every time you make a database call, every time you draw something from a cache cluster, every time you have to record that you're doing this, otherwise it won't show on your dashboards. And this is where these things get tricky, because of course it's easy to overlook exits. It's easy to overlook that you're changing a thread, for example, and you miss the current context of your trace. And you have to take care of all of this. Otherwise your information will be faulty and incomplete, and then your dashboards won't help you much more. So the library is fairly straightforward, but it's hard to get through straight. So the idea is that especially if you use frameworks and libraries that do heavy lifting for you, like if you use Hibernate for connecting to the database, or if you're using like a HTTP template abstraction to talk to the server, then these APIs have to understand your way of tracing. And that's hopefully possible if there's listeners and decorators for your outgoing calls. But if it's not, it can be fairly hard to do. So the idea was, I had some colors here. The idea was to create an API that everybody respects and that everybody implements, like a logging API, like a simple logging facade for J. That if everybody implements the API and offers it, you just inject your tracing context into it, and it will all automatically happen, right? So similar to Brave Open Tracing, which is not a tracer, a fully blown tracer. It's just an API, like simple logging facade for J. It offers the same sort of API and does the same thing. But that's where the problem starts, because the difference with simple logging facade for J, if 90% of your code is using SLF for J, then that's fine, and you have some very decent logging. But if the remaining 10% don't, and you lack, of course, these logs, which doesn't make the log itself unusable. But with tracing, it's more difficult. If you have a chain of 10 services and just one service in the middle isn't understanding your open tracing setup, then you still have no incomplete trace that breaks off after a few steps. So open tracing, in my eyes, is not necessarily the way to go forward. And actually, open tracing doesn't exist anymore. There was open telemetry and open tracing, and there's, to be honest, I lost a bit of overview of what it is, because they changed it so much that the API changes a lot. The name of the services changes a lot, and to me, this is a lost cause. But of course, it can work if you're very disciplined. But the cost of maintaining an open tracing or any tracing API implementation manually yourself, and then of course this is the Java agent person saying that, is too costly and too unreliable. Yes, there's some color more. So this is no, I haven't updated these slides in a while, since we don't have conferences. I'm not doing much talking, so. I'm not really, but this is like a 3-year-old slide, and open tracing doesn't even exist anymore. It did exist when I made the slide, so this was kind of a prophecy spoken for me. Of course, there's new standard coming, and now we have plenty of tracing standards, and no library really respects any of them consistently. So that's where we are, unfortunately, with these things, and maybe this will consolidate over time, but I'm sure at some point people won't be happy with the current tracing API and jump to the next thing. And I'm not saying this in bad faith. I'm just saying it's a really hard thing to standardize something that has to be basically include everything. If you can have gaps, it's much easier to establish a standard, because the standard is valuable even if it's incomplete. With tracing APIs, it's often not valuable to be incomplete. If just one context switch is missing somewhere, basically your software or your traces is not traced anymore. Right. So how instead can we implement APM on the JVM, which is the topic of today's talk? and of course the topic of or the expertise of my field, use a Java agent. And before we look into how you can use a Java agent to implement tracing, just a quick primer on what a Java agent is. So JVM has an API that's called the instrumentation API, which I think a lot of people have heard of, but few people really have worked with. And the instrumentation API basically allows you to create a jar file that is loaded before the actual program. So on the command line, when you specify the class path and the command line arguments at the program you want to run, you can also add another argument, minus Java agent, and then specify a single jar file. And this single jar file needs a manifest that points, instead to a main method, it points to a pre-main method. And the pre-main method takes a single argument of type string and, or optionally, a single argument of type instrumentation. And this instrumentation, in a way, is a gate to low-level functionality in the JVM, some of it at least. Like you can compute an object's actual size in memory, like in bytes, how much it consumes in heap, or it allows you to retransform classes, change the module graph, like things that are not normally permitted in an application, things that can be considered unsafe, not in the terms of memory leakage or seg faults, but unsafe in terms of possibly circumventing security manager conventions or breaking reflection boundaries and so forth, because it has some power. That's why it's not exposed in a standard Java application, because it would break the sandboxing model. But since it has to be specified in the command line, and since it's often useful to being able to break things for certain purposes, it's quite useful. The way transformation works, for example, which is one of the core functions of instrumentation, is that you can add a transformer, so-called class file transformer, which here receives a class loader and the name of a type, and maybe the type itself, it's already loaded, the protection domain, and the class file in bytes for every class that is loaded. So every time the JVM loads a class, you will be notified that this class is loaded, and you will get an opportunity to change the class file. So let's say that you observe as a APM tool vendor that the Apache HTTP client is loaded, the class for it. Then you can say, all right, this is interesting, because every time Apache HTTP client makes an outgoing HTTP call, I want to extract the current trace context and add a header to the outgoing call. And just like that, you have basically made Apache HTTP client compatible to open tracing, for example, without having made taking any actual action to it, right? So you basically bootstrap the functionality into it instead of having to wait that maybe the team behind the client decides to wanting to support your API. So when I was hired as a consultant to Instana, basically this was my task. Implement these two methods if you want. For every class being loaded, I had to decide if it's interesting for us, say true or right, this is interesting, and then if it's interesting, I have to take the class file for this class, add tracing logic, and then return the transformed class that you drop into a Java application, and off you go. Off you have a functioning, fully traced Java application. And in my eyes, this is the best approach. And this is also the approach most APM vendors have taken, because it's reliable and doesn't cost you as a consumer anything. You as a consumer, you can just say, right, this is something I want to do. I want to be able to just know what's happening in an app. I pay something for the product, but I save countless hours to not having to implement the logic myself, right? Just water. All right, not talking that much these days, right? Yes, and this sounds super difficult to do, because a byte array is a byte array. It's basically compiled Java code, a class file. But what you get is really, it's the class file. It's the contents of the .class file. And my library that I made, ByteBuddy, is basically a an approach to being able to read class files and to process them in a structured manner without you actually having to read the Java virtual machine specification that specifies how a class file has to look like. Because class files are quite easy if you want. That's a table, or off the table starts with the magic numbers, Cafe Babe, and then says like, all right, there's a class file and there's a constant pool saying like all the strings in the class, and then it says, all right, there's 20 fields in the class and 12 methods, and the first field starts at this offset and the second field starts at this offset and so forth. Then you can jump over the amount of bytes that were specified at the offset and see, right, this field is named foo, this method is named bar, and it takes these arguments and it contains these instructions, right? So basically, if you read the specification, it tells you what's what. And this is boring work to do, of course. And if you write in a tracer, you don't want to have one eye on the specification all the time. This is why high-level libraries like mine can help you out quite a bunch. And it's made for high performance, obviously, but it's also made for correctness. And especially in Mockito, Mockito got a bit slower when we switched to ByteBuddy, partially because ByteBuddy, it covers all the corner cases or attempts to cover all the corner cases, and respects generic type information, for example, which has something, which is important for some type hierarchy resolutions if you want to know what method overrides what method and so forth. And the idea is, of course, that ByteBuddy is always correct in its decisions and not only 99% of the time. That's something we learned the hard way, and that's something I have to really thank Instana for. They invested a lot in the library. I could try out some new functionality there as well. And in the beginning, we really crashed customer code as well sometimes, and that's very unpleasant if you take like a whole Kafka cluster down for some stupid bug that you made. So ByteBuddy intends to protect you from everything, from even verification errors, and I see them rarely now. And often if I see them, it's in conjunction with some other instrumentation library where something weird happens. And the slide also needs updating. Already supports Java 9. It even supports it, not only experimental. It very much supports Java 9, the module system, and it supports Java 17 even. And so if you've never heard of it, I'm not going to go through it fully today, of course. But it's a very comprehensive library, to put it mildly, and but with the intent to having fully safety measured code instrumentation API on the JVM. So, and how does a Java agent look like? So let's say right now, of course, I'm not showing you an example of the HTTP client, which would be just a lot of noise without educational purpose. I'm showing you a Hello World example. So what I want to do with ByteBuddy now is I want to change the class foo method bar to not return bar, but to return hello world, which is of course very non-intuitive, but possible. So the upper part is the program, and the lower part is the Java agent, and basically a premium method and its own jar file. And all you do is you create a so-called agent builder, which just ships with ByteBuddy, and you say the type named foo. And now assuming it doesn't have a package, transform it, take the method bar and intercept it to return hello world. That's how easy it is. And take my word for it, this can be copy pasted, and I think you have to add one argument there and transformer that I forgot or cropped out for readability reasons, but it's basically it compiles and runs. And there's plenty of examples on the webpage and other presentations and blog entries. So if you just Google it, it's fairly easy to get started. So, and that works. And of course, it's the perfect opportunity to know all of your coworkers, because this program is not debuggable anymore. Because even if you look at your source and you put a breakpoint in there, then there will be bar standing there. But the program will still yield hello world, of course. And but you're getting the point, right? This is just a showcase. And of course, you can mess around a lot. But of course, with APM tools especially, the idea is to just enrich behavior and not to change it really, right? Yep. Color. But how can we make something useful? So I think the most useful approach and the easiest way to implement a decorating agent that changes a method by adding some functionality is ByteBuddy's advice mechanism. And the way advice works in ByteBuddy is that you write a Java code and use annotations to tell ByteBuddy what this advice class is supposed to represent. Because this code is never executed, it's merely a template. So here you say we have a method enter and we have a method exit, and on the enter, on entering any method that is decorated with this advice, we want to call the code in the enter bit first, and then when we're done, we want to call the exit bit. And you can assume this is how you can implement a tracer, right? So here we say, all right, we don't only want to run some code, we want to access some environmental properties like the arguments of the methods we intercept. And then we extract a possible trace ID from the incoming request. We extract the method and the request URI. Then we can start a new trace if we don't find an existing trace in the header. And if there's one already, we just continue a trace with the trace ID. And then when the HTTP call exits, like here servlet, for example, then we complete the trace and we tell the backend like Zipkin that we have new information to showcase on the dashboard. And yeah, basically you just write this code. You can test this code, just as normal Java code, run it in a unit test. But then in runtime, you tell ByteBuddy, all right, any subtype of the servlet class, so anything that implements servlet, I want to transform and I want to advise to the servlet advice on any method named service of that, which is there typically just one. Of course, in production environment, you would have a more specific method that basically says, I just don't want it to be called service. I want to have this particular method with these particular arguments to make sure you get the right one, right? But what do you get as a result? And I'm just going back now quickly. You will have this code being executed every time that a servlet is called, and you will not have changed the application at all. And you will have covered every servlet in the application, even if you haven't known the servlet existed yet. So, and by doing it like this, you make sure that every servlet is really covered. There's not a chance in the world that you missed one if you do it right. Of course, it's always a chance to have a bug in your agent too, but at least you can test it as long as you want to see that the conceptual case is correct and that you're not discarding information. And that's the big advantage to having an instrument like this. You solve the problem programmatically that you would otherwise have to solve at every single location where it occurs, like with an explicit trace API like open tracing. Yes, and not enough joy, you can with Java agents not only instrument classes when they are loaded for the first time, you can also redefine them after they have been loaded. So Java agents have two approaches to attachment, and one is pre-main, where you have to specify something in the command line. The other is agent main, where you don't have to do this, where you can just attach the agent even after the application has started. And then if you do this, typically you say retransform existing classes. So what ByteBuddy will do then for you, it will find all loaded servlets that are loaded in the application and transform them as you go. And what you have to do for this, you have to tell ByteBuddy, which is an optimization, to not allow class format changes, because that's a limitation in current JVMs that you cannot change the class format. Like you cannot add fields, you cannot add methods, but with advice, you're just adding some code at the beginning and the end of every method. So then you don't really have to do this. Right, so and what you can do now, you can basically just find an existing Java program, you find the PID of the Java program, and then there's a tool in the JVM that allows you to inject this agent main method into the running process. So basically, let's say this can be used to debug a broken application in its broken state, right? You have an application that was running for a month, and then suddenly after a month it turns slow. You never bother to debug it, because after a month, who can wait that long to see a production to showcase? So then you just wait for this to happen, and then when it's running, you can still inject an observability tool into the JVM and extract the information you want. and then all you need to do is to write a small agent like this. Yeah. So, and that's basically also an opportunity to adaptively learn, because you have all these applications running, right? You have this one server with PHP and Java, and you have the other server with Java and JavaScript, and then Instana is basically running an application of itself, and finds all these machines that it has access to, injects the Instana agent into it, discovers everything that's running on the machine, like PHP and Java or JavaScript, and then it basically extracts all the data it needs to report back to the backend. And then even if you later find out that you're missing something while the application has been running for years, you can even patch the Java agent dynamically. Let's say like the customer complains, this one thing is missing from all my dashboards, and I know it's there, and you can look into it, hopefully find a bug, then patch the tracing logic, and then give feedback to the agent and update it, right? And I'm showing some terribly old screenshots now of the product, but then you get the same traces as in Zipkin, just a bit more, a bit richer, since we as agent can get much deeper into the JVM, and you can show these dashboards where you show where services hang together, and you can automatically detect where something goes wrong, so you don't show basically the symptoms, you show the root cause, hopefully. And then you can basically also over time check if something is off from the usual expectations. And of course, there's other products that can do similar things, but I think Instana has solved it pretty neatly. Yes, I have 18 minutes left, so these advanced topics are always like a bit to fly over, so I'll jump over a few slides now and then remainder to being able to answer a few questions if there's any, and if not, then I just pick up more advanced topics or go to bed, because my kids will get up early. But yeah, adaptive sampling is something interesting to know about, because a lot of products, many of them claim they don't have adaptive sampling, but to some regard they all do. So basically, whenever you have a call coming in, you wonder, do you keep it or do you trash it? Because if you have millions of calls coming in, you can of course try to batch them to record them as multiples of the same trace if they are similar enough. But sometimes you just have to throw away data, because sometimes if there's a if there's a high pressure event, then you have to kind of draw back a bit as the monitoring tool to not make too much trouble to the actual performance. So because of course any machine has a trade-off between observing and doing, and since it's running in the same process, there's limited resources you have to share, right? But you should typically batch and install this quite well, actually. So basically, we try to aggregate data if it's similar enough to then send it rather up to the SD aggregate, so you can still keep the most interesting traces, but the least interesting traces you don't really have to keep. But it's nice for aggregation data. Then you can still in the buffer throw out things if it's not, if it's too much pressure. Yeah, so typically that's the thing. If you have like very little traffic, then typically you don't want to sample adaptively, and you want to capture everything, because maybe you're testing something, right? You want to see how it plays through the traces, so then you don't sample adaptively. And I think actually Instana changed this also, but as a first version, when back in the days, this is basically how it worked in the early version. At least I have no idea how it works today, actually. But yeah, and the more requests you have, basically the more you have to track back, because then typically you're only interested in the high pressure events or the off events, and ideally you can detect them when you decide what to keep. Yeah, then you have always this overhead argument, and I find it's very difficult, and I understand marketing is hard, and all this competition, you have to basically make promises that we have maximum 1% overhead, but these numbers don't really mean anything if you look into how JVMs work, because if you have an app that hands web requests all the time, then the app is super busy. Then if you're monitoring web requests, you will of course add overhead to that app. But if the app just sleeps around and doesn't do anything, then there's nothing to monitor, and you don't have overhead. So it really depends on the traffic, and all these benchmarks are kind of like pitched in the direction that it gives you a good result, of course, and that's always the case. But I mean, there's overhead, of course, but JVMs typically aren't at their maximum. So, and especially if you trace, you can be smart about it. You can like see the things you're already observing, right? So if you see you're very busy or the CPU is running out of availability, you track back a bit and you free CPU. But if there's 25% free CPU all the time, then these 25% CPU are basically free. You can use them without interfering with the app. And then with network traffic, it's the same. You can see like just store some in memory as long as you have enough, and then send it when the pressure's off, right? Just skip over the moments where there's suddenly thousands of requests coming, and if this is just like for 2-3 minutes and then it goes down again, then you know that since you're a tracing tool, and you use this window of opportunity to send out your data then. Yep. So basically, yeah. So and that's also like what's overhead. If you're in the cloud and you have a very scalable machine, and you might have 0% overhead, but that's because the cloud automatically scales, and then it just costs you a bunch because your AWS bill gets higher. And if you have the same thing on your local machine and you just set it on fire by adding the trace, and your process falls over, so that makes this marketing even more valuable as a number. So if you add an APM tool, you have overhead. Just it's there, and hopefully the tool's smart about it. But yeah, the more data you get, the more overhead you'll have. It's as simple as that. Another thing is if you implement Java agents, JIT-friendly tracing is important in a way, because let's say like typically if you have a web request that's coming from native layer, that's like C code dispatching the IO, and then it enters Java, right? And then you send it out again, it exits Java. So this part is like the stack bit that's getting optimized off the JVM. And JIT optimization is built on heuristics. So let's say a method is of that and that size. If it gets too big, it's not optimized anymore. Especially that's an important thing to remember. So if you add a lot of code at the beginning and the end of a method might get that big that the JIT optimizer doesn't kick anymore. And then basically this green, nicely optimized code field will get blown apart into 2 pieces or into no piece, worst case. And then suddenly your Java agent has made the program a lot slower, not because of the code you added, but because of the heuristics you have changed. So ideally, as a Java agent, you always want to go close to the C layer, because typically, so like by experience, those areas aren't so bad to mess with, so you don't disturb the JIT optimizer that much. But of course, ideally, you don't have to count bytecodes of every method you approach if you're already in the red area of too big of a method. But that's something to keep in mind if you write agents, that you have to stay away from the nicely optimized centerpiece of call stacks. Yes, and you can control these inline limits and so forth, and the inline levels, but typically it's not a good idea. And especially if you're writing a generic agent that's deployed into thousands of applications, you don't stand a chance to keep an overview of what's best for your particular customers. Jump over this, and yeah, monomorphism is important and nice, but maybe too big for 10 minutes. Memory fill tracing. This is from Zipkin. They changed it after I complained to them that it's not a good idea. But like all the optional values here, for example, in Zipkin were the early versions were wrapped because they can be null, right? You can not have a parent ID. But the problem is then that once you assign one, you allocate objects. So it's much better to remove all this stuff, right? For example, to have a parent ID where long 0 means nothing, right? A default value, and just forbid the trace ID of 0, which is easy enough, right? The same for timestamp duration, just set it to 0, meaning nothing, and then you have primitive values, much better. Same like with annotations. It's if you have a list and this list grows and so forth, if you know that traces never have more than 5 annotations, just have 5 fields. You save the overhead of the list, and just avoided strings, especially, also a good data type because they get pulled easily. And also volatile is a bad idea because has memory model implications that might cause synchronization between CPUs and stall things. So stay away from volatiles, stay away from wrappers or objects in general. And actually in Instana, basically we use object pooling for a lot of things still, because it takes a lot of pressure from the JIT. And this is, of course, ugly code to write, which is another argument in my eyes against explicit tracing APIs like open tracing, because with the Java agent, since you already generate the code with templates, you have a lot of opportunity to hide the ugly stuff from your daily code. But if you put exploded objects, meaning like you don't have a trace object, but you have like 4 primitives on the stack just to avoid an object allocations, that's ugly to debug with and to work with in development. So it's better to extract it out in my eyes again. So so hopefully, I mean, it's not entirely a zero garbage tracer, but it's a low garbage collector, and that really shows if you compared. More color. That's one we can also. So one other hard thing with tracing, and I think this is the most overlooked one, is you don't only have to instrument entries and exits, you have to instrument all context switches within an application. So if you have an incoming thread trace and you want to remember that this basically is a current trace, and you fire through something like React, right? Then React will spin up hundreds of threads and ping pong your requests back and forth. And you have to kind of remember that this React input was supplied by this one incoming request, and you have to propagate it. And then I think while implementing code for Instana, I spend way more time instrumenting fork join pool, nightmarish instrumentation, all these, or React or Akka. And those are the hard parts, and those typically don't care for frameworks and APIs that do web tracing, of course, because it's not their main domain, but they are a very central aspect too of it. So this is definitely a difficult part when it comes to tracing. So, but you can get it right, and a lot of modern tracing solutions do get it right. So we have to get in there too. And that's it for me. Thank you so much. We have 7 minutes for questions. Otherwise, you can find me on Twitter, on the web, you can find ByteBuddy on ByteBuddy.net or on GitHub, and there's another library I maintain documents for Jay. And of course, other stuff. You can find all on my GitHub and my webpage if you're interested. And follow me on Twitter if you're interested in these kind of topics. And thank you so much for staying up so late with me if you're in the same time zone, or joining into this last session of this conference. And thank you so much for having me.
Thank you, Rafael. We have a couple of questions. One of them you probably already went through, which was about the overhead of the agent code wrapped around the monitored methods. I think you covered this. If you want to say a couple of more words.
So the nice part about this is that when you use advice, at least what ByteBuddy does, it doesn't call the agent. It basically copy pastes the code into the original method. So of course it takes as long as it takes to execute the code, but it's JIT optimized normally, and if you do it right, you basically just extract a little bit of data, and then you push it into a buffer, and then you consume the buffer from another thread. So ideally you don't want to consume any resources on the user thread if possible. So it's small, but it's there.
Another question is this one. What do you think about fault tolerance, and what your practice to solve fault tolerance problems?
So I understand the question, like you're wondering if you should use agents to insert fault tolerance, like that you recall a method if it fails. And that's definitely something you can add. But I would ByteBuddy as a build tool then. So you can like add an annotation and say like trial 4 times, and then basically you add an advice that calls the method, catches the exceptions, and spins back to the original code. And that's definitely something you can easily implement at ByteBuddy. but then you won't have it in tests, which might be just what you want. So you can have it in tests if you run it, like if you put it into your Maven build, for example. But yeah, it really depends. But I think typically, like with lambdas and so forth, you can also do this in lambdas quite nicely. So maybe that's often a better solution.
So I have a question kind of related to this. Is like, do you recommend any particular style for writing these, let me call them aspects? In the sense that, for example, it would be better to do something like you have shown in the example, meaning search for servlets and then add an advice to the service method, rather than maybe saying, okay, I know exactly where I want my tracing to be propagated in the code. Let me do this. I'm going to put the code that sends a request through HTTP client into a method. Then I'm going to annotate the method with a, let's say, business annotation. And then the aspect goes and look for that particular annotation. I think this is easy to do with ByteBuddy, right? So basically, it's kind of a mix where you are aware that there are specific points in the code that you want to annotate with a tracing annotation which belongs to your code, and then the aspect just uses these annotations to be more precise in pinpointing. Because the other question that I have is that since I've done aspect programming in the past, it was like the biggest problems were the compositions of the aspect. Maybe you had like 2-3 aspects that you forgot about, and then you had a fourth one which happens to actually intercept the same set of methods or fields or whatever that the other 3 that you forgot about were doing. And now suddenly your one-line method becomes one line plus 3, 4, or 5 aspects, and then you don't understand what's going on. I mean, you don't understand anymore what you're measuring, right? Am I measuring my code, or am I measuring my code plus an aspect plus another aspect, or what is it?
So quite honestly, I always found AspectJ is a fine tool, but it always felt foreign to me. So it's like having its own language and having these point cards and join points and everything, and like a string-based interception language. So I always preferred this explicit DSL where you basically just on the ByteBuddy you can say that like all types matching this, and then do this, that, and that, and you can actually say and don't match any previously defined matches. So it's more open to a declarative style where you basically instruct what you want. But of course, that's one of the hardest tasks about instrumentation generally is like the whole identification aspect. And if you put an annotation on your code, for example, that you want to instrument, then you can do this with if the user interacts with your agent. Like if you offer an SDK for instrumentation, you just say like span, and you annotate a method with span, and all these methods will be matched. But like the Apache HTTP client people, they won't do that. They won't answer to the 20 frameworks. They want them to integrate against them. They just say like, yeah, we have these APIs. You have to integrate against us. We just offer this point where you can like inject yourself. But we won't have an explicit dependency in your code, which I think is a fair argument. Because if Apache HTTP clients, if they make dependencies on these, like the good thing was simple.
I was not advocating for that. I was more advocating. I was more advocating for something like in your business code, you refactor the code that actually uses HTTP client into a method in your code, and then you annotate that method, not HTTP client.
Yeah. So, the problem is then like anybody then using Spring, and Spring uses HTTP client on the covers, and then you would have to do it there, and you have to find out how this works. But it's also a legacy code base, and it's a million lines of code, and nobody has an overview, and you just still want to see it because your other service interact with it. So like from a business perspective, typically everything's a mess, and everything needs to be done as soon as possible at low costs. And then it's nice to just being able to come from the outside and say, like, you know what, I defined all the rules in the agent and you don't have to do anything. But if you want to add something to the standard libraries that we know of, then we also offer you this SDK where you can interact with our agent if you want to, but you don't have to. So that's, in my eyes, the best way of doing it, is to offer it, but to not make it mandatory. Because then people can also, like, I mean, from a sales perspective, it's nice if you can just say, like, here, try it, drop it in, and if you don't like it, take it out again tomorrow. Then that's a good sales argument. If you want to build a product, that's something you have to think about quite early on.
Indeed. Okay, so that was the last question from the audience. I think we can call it to an end, and it's a wrap. So thank you again for your presentation. And
thank you so much for having me, and thanks to you for hosting.
Yep, be well.
Cheers, take care, bye-bye.